Special relativity. Light ray that reflects back in inertial frame and does not reflect back in another inertial frame moving relative to the first frame. At time t1 equals t'1 equals 0, a ray of light is emitted at point p'1. The coordinates of p'1, p'2, p'3 are the following. From the Pythagorean theorem, we can find that the distance from p'1 to p'2 is equal to 50 c. The ray reaches point p'2 at time t'2 relative to observer k'. The angle of incidence and reflection relative to k can be computed from the arc-tangent formula. Theta prime equals 36.870 degrees. The ray reaches point p'2 at time t'2 relative to observer k'. Observer k', compute the time period the light ray reaches point p'2 as follows, from which we find that the time interval t'2 minus t'1 equals 50 seconds. Observer k', compute the time the light ray travel from point p'2 to point p'3 depending on the fact the light travel at constant speed relative to any observer. From which we find that the time interval t'3 minus t'2 equals 50 seconds. Assume that frame k' is moving at speed 0.8 c, the Lorentz factor will be gamma equals 1.6667. The time the ray takes to travel from point p1 to point p2 equals p'2 relative to observer k can be computed according to the following equation shown in task 10, and it is computed and found to be t2 minus t1 equals 136.66 seconds. The time the ray takes to reach p'2 relative to frame k is t2 equals 136.66 plus t1 equals 136.66 plus 0 equals 136.67 seconds. We can apply the spacetime transform at point p'2 to reach the same result. P'2 coordinates are x'2 equals 40 c meters, t'2 equals 50 seconds. The corresponding coordinate of point P2 in frame K can be computed and found to be T2 equals 136.67 seconds, x2 equals 133.33 c meters. The ray reflects to point P'3 at time T'3 relative to observer K'. The time the ray takes to travel from point P2 to point P3 equals P'3 relative to frame K is computed according to the following equation shown in task 10 and is found to be T3 minus T2 equals 30 seconds. The time period the light would take to travel from point P1 to P2 to P3 according to K will be T2 minus T1 plus T3 minus T2 equals 136.66 plus 30 equals 166.66 seconds. We can apply the spacetime transform at point P'3 to reach the same result. P'3 coordinates are x'3 equals 0, t'3 equals 100 seconds. The corresponding coordinate of point P3 in frame K can be computed and found to be T3 equals 166.67 seconds, x3 equals 133.33 c meters. The time period the light would take to travel from point P'1 to P'2 to P'3 according to K' will be T'3 minus T'1 equals 50 plus 50 equals 100 seconds. We can compute the time period the light would take to travel from point P1 to P2 to P3 relative to k according to time dilation formula, since we are measuring the time interval for one clock, which is clock A prime, in frame k prime using two clocks in frame k. T3 minus T1 equals gamma times T prime 3 minus T prime 1 equals 166.66 seconds. The distance the ray travels from point P'1 to point P'2 according to k' can be computed according to Pythagorean theorem. L'12 equals 50 c. The distance the ray travels from point P'2 to point P'3 according to k' is equal to distance L'12. L'12 equals L'13 equals 50 c meters. The distance the ray travels from point P2 to point P3 over x-axis relative to observer k can be computed according to the formulas we derived in Task 10. We apply the formula and find x2 minus x1 equals 133.33 c meters. The distance the ray travels from point P1 to point P2 according to k is L12 equals 136.66 meters. The distance the ray travels from point P2 to point P3 over x-axis according to k can be computed according to the formulas we derived in Task 10 and is found to be x3 minus x2 equals 0. The distance the ray travels from point P2 to point P3 according to k is L13 equals 30 c meters. The tangent of the angle of incidence relative to k can be computed according to the formulas we derived in Task 10. We have computed the angle of incidence and reflection θ' and found it to be θ' equals 0.6435 radian. We substitute that in the angle of incidence formula, from which we obtain θ12 equals arctangent 0.225 equals 0.22131 radian equals 12.68 degrees. The tangent of the angle of reflection relative to k can be computed according to the formulas we derived in Task 10, from which we find θ13 equals pi over 2.